What is that? Oh, to do that. All right, so this is what you should have obtained with completing the square twice and then dividing the right-hand side to equal 1. Now, I've placed the part of the equation that never changes. If you are looking at the formulas now, which I encourage you to do that, we have a vertical and a horizontal, and this part of the general equation is the same for both. So at this stage, we are going to use the numbers to determine which one we're looking at. Are we looking at a horizontally oriented or a vertically oriented major axis? Vertical, because the largest number is under the y. And so this is going to be a squared, and this is going to be b squared, because a is always larger than b in the formulas. Okay, that's how we define a and b. The larger number is a. And you'll see that on your formula sheet at the bottom on this page where it says where a is greater than b. That's the formula. So that being said, notice also in the formula that these two denominators are written as perfect squares. These are not. So to write 9 as a perfect square, we would square what number? 3. So b is 3. And therefore a is 5. So now we've determined all of these pieces. And what is HK?
4. Yeah, is it 4 negative 1?
4 negative 1. Good. Right? So first we complete the square twice to obtain the standard conic form for an ellipse, from which we can gather a whole lot more information than we could from the general conic form, which is just a giant mess. So this is the graph of that ellipse. And so what I'm going to do now is I want you to calculate C, but first I need you to make sure that you have a yellow and an orange highlighter. And if you do not have one, I'm going to bring around, that's why I insist on the use of color. What did you obtain for C using this formula?
4.
4, very good. Notice it looks similar to Pythagorean theorem, but not quite. So what we would actually do here, this would be 5 squared minus 3 squared, and so we would get 4. So the next thing I want us to do, now that we have identified the center HK, the value of A, the value of B, and the value of C, which we haven't discussed yet, is let's highlight the major axis in yellow. And then highlight the minor axis in orange. After we get those highlighted, I want us to label certain other structures. So the first is the vertex. Right, so the vertex, you can label both or one, whatever. So there's a vertex at the ends of the major axis. What is the name of this point? What is this called? Co-vertex. Very good. Co-vertex. How many co-vertices are there? 2. Right? This other point hanging out here is the focus. If you remember from our string applet, this is the location of those 2 points you were moving around. Those are the foci. So this is a focus and this is a focus. Notice it's still getting hugged by the curve, just like it did with the parabola, right? It's still right inside of that little, inside of the curve, not outside. So the values A, B, and C correspond to certain distances between certain features of the ellipse. So based off what you learned when we were doing the exploration, the distance from the center to the vertex should be what letter? A, right? Because that's half of the major axis. So what then should this length be labeled? B, half of the minor axis. Now the only one I haven't shown you yet is what the length C corresponds to, and that is the distance from the center to the focus. So knowing all of these distances is very similar in practice to how we use the distance P with the parabola. They are distances from and to certain structures within the ellipse. So if we know the center, HK, and A, B, and C, we know everything we need to know about the ellipse, okay? Just like with P, except now we have more parameters that we need to find in order to form this shape. So let's kind of summarize that here. A is the distance from the center to a vertex. B is the distance from the center to the what? Co-vertex. And C is the distance from the center to the focus. Very good. So all of these kind of branch out from the center. And you can find all of these other structures by moving up and down or left and right from the center, A, B, or C units. Now, I will caution you, these are some nice numbers, and I chose these intentionally to be nice. They're not always nice, especially C. A and B will generally be nice. C will sometimes not be because you're working with a square root, right? And that's okay to get a decimal for those. Usually your numbers will be fine for A and B because they have to be a perfect square. All right, you'll still need your yellow and whatever because now we are moving on to the hyperbola, which is the most complex of the conic sections. So, another type of conic section is the hyperbola. We define, just like we did with the ellipse, the hyperbola in terms of distances from the two foci, except now, instead of the sum of those distances, the criteria for the hyperbola is that the non-negative differences not the sum of the distances, but the difference of the distances. That is a tongue twister. Difference of the distances. So we will not delve too deeply into that because it's a lot more difficult to conceptualize, but you can see the two orange pieces in that small graph are distance 1 and 2, and so the difference between those has to stay constant. So again, the general form of any conic section. And from that general form, we complete the square twice to get these structures. You'll remember also from your board work on Friday that sometimes you ended up with a minus. That is the hyperbola. It's the difference in the distances versus the sum. You'll see plus in the ellipse, minus in the hyperbola. That's how you can differentiate the two. The other thing that we need to talk about is how we tell the difference between these two formulas. In the ellipse, we told the difference based on A and which value was larger. That is irrelevant in the hyperbola. So if you see subtraction, you have a new set of rules. What you need to notice here is that in the vertical axis, and we'll talk about what a transverse axis is in a minute, but in the vertical one, the y part of the equation is positive. And in the horizontal axis, the x part of the equation is positive. So let's write that here. The y is positive. Over here, the x is positive. I know that this is negative because there's a negative in front of it, right? It's subtracted, which is the same thing as adding a negative. So we consider this term to be negative. I'm looking for the positive term to determine whether this is vertical or horizontal. So now I'm going to talk to you a little bit about the graphs. And at this stage, looking at this graph may be a little overwhelming. That's why I pick it apart piece by piece instead of just showing you this because it's awful. But there are a lot of parallels between what we've already looked at. If you notice, the actual graph of the hyperbola itself are the dark, solid blue lines. It looks like two parabolas facing away from one another, right? These parabolas together make the graph of the hyperbola. They have vertices in the normal location. The vertices of the hyperbola are located exactly where you would expect, here and here. The foci are here and here. Once again, exactly where you would expect from the parabola. And then we have some other structures we'll discuss in a moment. The transverse axis, we don't have a major and minor now. We have the transverse and the conjugate. The transverse axis connects the vertices. So notice how this is the vertical transverse connecting the vertices. And this is the horizontal transverse axis, again connecting the two vertices. Okay? So if you know Pisces, like if you're an astrology nut, and that's what so from there, these orange dotted lines are asymptotes. Okay? Every hyperbola has it, and it has two of them, and these are the equations to find those asymptotes. But don't be sad, because it's just H, K, B, and A, which is very easy to find. We've been working with H and K and B and A already. We know those are not difficult to find, and then it's just a matter of plugging those things in there once you find them. Distance to the foci. C is calculated with a different formula. Remember, it was kind of like a wonky Pythagorean theorem before? Well, it is the exact Pythagorean theorem now. And I don't want you to freak out, because I'm going to give you all of these formulas. You just have to know how to use them, how to tell which one's vertical and which one's horizontal, okay? But I'm going to not make you memorize all of these things. You just have to know how to move back and forth between all this stuff. Anyway, yeah.
Everything on the pages before this is for ellipses.
And then when you see the headline, look right here, hyperbola, that is when we begin the hyperbola section. All right, now I'm going to give you another 3 or 4 minutes to find the standard conic form or a hyperbola. Complete. When you completed the square twice is what you see in the left in black. This is most likely what you came up with, right? But recall that the formulas I gave you are in this format with subtraction. So in order to do that, we would just switch the order. And so this would become positive y whatever minus x whatever. Does that make sense? Yeah. Now this looks like this. Remember, this is all about making this look like this so I can pull certain values out that become obvious. So what is the value of A?
9.
3.
3.
Oh, 3. Very good. That's all right. What is the value of B? 2. Now, one thing to note here is that the A term, the A square, is always under the positive. Okay? So in the ellipse, the A always stays first. You may just adjust this part. Okay? So, but remember, this is also a perfect square. So 9 is equal to A squared, therefore A is equal to 3. The square root of 9. Right? And then what did you obtain for C? Not a decimal, exact value, please. Square root of 13. Okay? So let's record all of those things, because what's going to be helpful to you here is recording A, B, and C, and is also HK. So A we said was 3, B we said was 2, C is the square root of 13. And so the center, HK, let's talk about that for a second, would be where? -5, 4. This works exactly the same way as it always has. Where is the center? -5, 4. Now look where the center is in a hyperbola. It's right there. Okay, I'm not going to bother putting that there because I feel pretty confident that we can remember where the center is. So now, the transverse axis connects the vertices. Highlight it in yellow. And label the vertices. So this is a vertex. The conjugate axis connects the co-vertices. Notice there are some parallels forming between this and the ellipse now. highlight that orange, and label a co-vertex. So does this hyperbola have a vertical or horizontal transverse axis? Vertical. How do we know from the equation?
The y is positive.
The y term is positive. Exactly. And this is what that looks like. So just like the ellipse, the values of A, B, and C correspond to certain distances inside of the hyperbola. So this value from a vertex to the center, based off what we saw with the ellipse, what do you think that's going to be? A, B, or C? A. The distance from the center to a co-vertex is going to be B. And the distance from a focus, which is this, remember the focus still looks like it normally does inside of the curve. The distance from the center to the focus is C. Exactly. So these, you conceptualize it in that way, as these distances between center, vertices, co-vertices, and foci. The A, B, and C pretty much do the same thing with both of those. So again, let's summarize. Yes, ma'am.
So then if the y was negative and like the x is positive, then we have a vertical transverse axis?
We currently have a vertical transverse axis.
Okay,
Yeah.
wow.
Yes, correct.
Okay.
Correct. So the parabola pieces would open side to side.
Okay.
Right? Okay. So A is the distance from the center to a vertex, and we're just summarizing here. B is the distance from a center to a what? Co-vertex. And finally, C is the distance from the center to a focus. All right. Now, one quick thing I want to point out about this graph is it has something extra that we haven't discussed. We've discussed the graph itself, which this is the hyperbola, the solid line, the focus, the vertex, the co-vertex, the center. We have not talked about this rectangle. Rectangle is just a guideline box for your asymptotes. Okay. Notice the asymptotes will always, if you make a box that includes the vertices and co-vertices as the midpoints of each side, you will have your guidelines for your asymptotes. But most of the time you will not be pulling them from a graph, but we use this and you will see it. So I want you to make that connection. They go through the corners. In order to write the equation of the asymptotes, remember in the beginning I told you that what you needed was H, K, like A and B. So now what we're going to do is we are going to write the equations of these. So we are going to need, let me write it down here so I can see it. A equals 3, B equals 2, HK is negative 5, 4. All right, let's go pull the equation for the asymptote. This is a vertical transverse axis. So the equation of the asymptotes are located at y minus k equals plus or minus a over b times x minus h. You'll recognize this maybe as the point slope form of a linear equation because it uses a point and a slope. So we call it the point slope form because we're boring. So now all that's left to do though is put in k, a, b, and h, which we have. And then it's a small algebra 1 style leap to get it to the form I want it. So this would be y minus 4 equals plus or minus. A over b is simply 3 over 2, x plus 5. That's it. So now all that's left to do is notice my instructions say write the equations in the slope-intercept form y equals mx plus b. So what you do there is you're going to need to, first there are two equations here. I'm going to take the plus, the positive slope. Right? And then I also have a negative slope, negative 3 over 2, x plus 5. All right, well, if I'm going to isolate y and make this look like the slope-intercept form, I'm going to have to distribute this 3 halves to unlock all this. So I'll have y minus 4 equals 3/2 x plus 15 over 2. Now what's the last step I need to perform to isolate y?
Subtract 4.
Add 4. So that's going to be 3 over 2x plus, was that 23 over 2?
Yeah.
Yeah. Okay. Am I in y equals mx plus b?
Yeah.
Yep. Let's do it again over here. Now with the negative slope. We'll distribute the negative 3/2. We'll have negative 3 over 2x minus 15 over 2. Adding 4 to both sides, we'll have negative 3/2 x plus 8 over 2, the minus negative 7/2.
Yep.
How can I do that and not 4 times 1? I don't know. It's a mystery. Anyway, there are your slope-intercept forms of your asymptotes. And that is the last part of the skill for hyperbola. And so here is kind of why the